Last week we talked about linear regression, and we talked about linear regression as an example of supervised learning. When we think about learning or about machine learning, we normally think of a training data, a data set on which we estimate our model, and then some test data on which we test whether the model works well. So we typically do not want to use the same data for both. So in supervised learning, in the training data, we know the classification. So we know whether particular countries or cases score high or other cases score low, and then we can see what other variables correlate with this high and low values. So that's what we can do with linear regression. Linear regression you can think of as a context where also a scatter plot would work. So you have two scale level variables, one that you try to predict or explain, another set of variables that you try to use to do the explaining, and then you see if there's a relationship between those. Now, logistic regression and some other models that we will discuss in this lecture, they are closely related. They fall under supervised learning. They are more or less regression based, depending which model we look at. But the difference here is that the variable we are trying to predict, the variable we are trying to understand, is a binary variable, and by binary I mean there are only two answer categories. So in the lab, for example, we might look at democracies and non-democracies and try to see what features of a country make it more likely to be democratic. Or if I were to work in a factory, I might think of faulty products and correct products and try to predict when they are faulty or not. When I'm a bank, I might want to see what properties, what features of customers or their behavior is more likely to lead to default on a loan. So I have a binary dependent variable, default or not. I can look in the past. I can look at all the loans over the past decade and all kinds of data I recorded on the individual customers and try to see what the relationship is. And then maybe in the future I have an early warning system. I can predict which loans are likely to default based on these characteristics. So this kind of model where we have a binary outcome variable, vote, did not vote, democracy, non-democracy, war, no war, bank loan default, no default, and so forth. These are the kind of models that we're trying to understand here. An important difference here is that in a regression type of context, we are thinking about predicting the mean. So you have to be a little bit careful with the vocabulary here because it's a bit different in the social sciences and in the machine learning world. So in the social sciences, we talk about regression when we try to find what variables explain a particular outcome variable. And we have all kinds of regression models. Multi-level regression, linear regression, spatial regression, logistic regression, and so forth. And for all of those we think of regression, where there is some outcome variable we're trying to explain based on a set of independent variables. In the machine learning world, they make a bit more strict distinction between regression models and classification models. Regression models are those models where the dependent variable, the variable we are trying to predict, is a scale level variable. And what we try to predict is the average or mean level on that variable. So we try to see how for different groups or cases with different features, the predicted mean on that scale variable might be different. Whereas we talk about classification when we have a categorical variable that we try to predict, and we try to predict how likely it is for any case to be in that category. The phrase logistic regression in this context is a little bit of a misnomer because we are really talking about classification, not regression in the machine learning language. And so last week was about regression, this week about classification in this terminology. Now throughout this lecture we are going to look at this example data here. So this is fake data, it's data just generated by a computer. There are no real variables here. But one thing is very important, this plot is going to be a little bit confusing at first because you really need to think of it as a multi-way graph. You've seen multi-way graphs before. So with linear regression, we often think of the x-axis as the independent variable, the y-axis as the dependent variable. But this is not how it is displayed here. So here we have two independent variables, variable 1 and variable 2, which are on the x and y axis. and then the color of the points shows you the y variable, the classification of the points. So we want to find, we want to predict best the classification between these black and gray points based on those values on variable 1 and variable 2. So we're going to look at different methods to classify observations based on variable 1 and 2 into these two groups. And so the dependent variable is in the color here, not in the y-axis, and the independent variables are in the axes. So here this is just enlarged a little bit to make it more clear. Yeah, so you can clearly see that we have two groups. We have these black points and we have these gray points. And we are trying to see to what extent we can predict whether a point is black or gray depending on what we know about variables 1 and 2. And you can already see, of course, that there is a lot of overlap too. So a lot of points are in the same region in this plot, and so knowing the value on variable 1 and variable 2 will never give you a perfect prediction of the dependent variable. When we code a binary variable as just zeros and ones, and we call this a dummy variable, I think we discussed this when we talked about linear regression, and it was the independent variable. When we do that with the dependent variable, we can actually run a linear regression as well. So we can run a linear regression where the outcome variable is only zeros and ones, and where the independent variable are any scale variables or dummy variables. You can see an example here in front of me. So you can see how when you make a scatter plot and the variable is coded as just zeros and ones, all the values are of course on the line. They're either on the line at 1 or on the line at 0. And we can estimate a linear regression, and it will just plot us, estimate a straight line through this. It does give some strange predictions. It can predict any value between 0 and 1, even though only zeros and ones are correct values. And it can even predict values outside 0 and 1. We can nevertheless use this for classification tasks simply by deciding on a decision criterion when we predict a 1 and when we predict a 0. For example, the dotted line here is at 0.5, and we could say that whenever we predict a mean above 0.5, let's predict a 1, and whenever we predict a mean below 0.5, let's predict a 0. And then we have a classification algorithm. So we can use linear regression when the dependent variable is a binary. And we normally call this the linear probability model because the estimated means, they look a bit like probabilities, as they are typically between 0 and 1, but not necessarily. And they suggest, and if they are higher, the chance of observing a 1 is higher, so they are a bit like probabilities. In political science, this is quite rare. In machine learning, it's fairly common. In economics, it's also fairly common. Now, this plot that I just showed you is it looks like a normal linear regression, right? We had the independent variable on the x-axis, the dependent variable on the y-axis, but it's only for one x variable. We were going to look at this plot of x variables, where the x variables on the axis and the color is the y variable. So on that kind of plot, we can draw a decision boundary. We can draw a line that is the threshold between predicting a 0 and a 1. And so you can see how the predictor works. When we assume that the threshold is 0.5, you see the threshold. This green line is the prediction of a linear probability model when we use these two variables, x1 and x2, variable 1 and variable 2. And this line is the decision boundary between predicting a 1 or predicting a 0. So above this line, we predict everything to be gray. Below this line, we predict everything to be black. And of course, a lot of predictions are wrong. So any gray point below the line or any black point above the line is misclassified. Our estimator does not properly classify those points. But on the other hand, it does not do too bad a job. Many of the points above the line are indeed gray and below the line are indeed black. So the linear probability model leads to this decision boundary that you see displayed here.